Hi, my name is Zhijia Chen, a PhD student from Temple University. Today, I'm presenting Web Record Extraction with Invariance. The paper is co-authored with Professor Wei-Yi Meng from Binghamton University and Professor Adil Jagut from Temple University. Web records are structured web data retrieved from the underlying database and displayed on web pages according to some templates. In the field of web record extraction, there are generally two types of tasks. One is extracting web records from a list page that contains multiple web records in a list-like fashion. Our work falls in this field. And the other is extracting specific attribute values from a detailed page. For example, we might be interested in the title, rating, and the price of a book. And in this case, the target page presents a single record. When we examine the existing solution, we found that they are based on some outdated assumptions. We summarize three assumptions that are frequently taken by existing methods. They are homogeneity, linearity, and continuity. The homogeneity assumption says that all records in the same data region have the same schema. As example shows here, in the old days, the result of search engines are simple. Each record consists of a title, a snippet, and a URL. But these days, a search engine like Google may tailor the representation of a record according to its entity type. For example, they may have cover images and present key attributes that the search engine has recognized in the page. Here we make the distinction between Old Web and Modern Web. Old Web refers to Web 1.0, where the web pages are static and simple, and Modern Web refers to Web 2.0, where web pages are dynamically loaded and much more complex. The linearity assumption says that web records are presented in a linear list-like fashion. This is violated on modern web because some websites use nesting structure to group records from the same website, as example shows here. Or some websites may use the nesting structure to indicate the hierarchical relationship like comments. And the continuity says that web records in the same data region are continuous. However, on the modern web, advertisements and some other related data are frequently inserted among web records. For example, on the Amazon page on the right, there is an advertised item that spans across the page, and the advertisement contains a video to show the product. To have an intuitive idea of how modern web records have evolved, we show two examples of web records of search engines. The left side is a search engine result page that collected 20 years ago, and the right side is a result page collected recently. We visualize the web data records by transforming a web page into a sequence signal. We will talk about the transforming technique in the next few slides, but now let's see the differences between the signals. We see that the signal of the left side are periodic with regular patterns. However, for the modern web records, it's hard to observe any periods, but still, as shown by this red rectangle, we notice that there are some subsequent patterns that are frequently appear through the signal. So we ask, what contributes to these frequent patterns, and can we leverage on this pattern to extract web records? So, with these challenges in mind, we propose a new web records extraction method by detecting some invariant structure among web records. We name this method as MIRIA, which stands for Mine Record Invariance. We observe that despite the structural irregularities, web records are generated by some templates, and thus they must exhibit some common structures they contributed by common attributes or common styles. We argue that we can no longer measure web record similarity at record level, but at sub-record structures, and we try to use those sub-record structures to detect and recover web records. We will introduce our method with a running example that reflects the three violations of assumption that we see previously. In this figure, the left side is the visual presentation of examples that we see in the browser, and the right side shows the DOM tree. Each node on the DOM tree is an HTML element. They consist of the tag, the attributes, and the text content. This example consists of three web records they bounded by the red dashed lines, and they correspond to three subtrees. The web records 1 contains an image that does not exist in the other two records, and the record 3 is nested under record 2. We will first need to define a container node. They are the target nodes that we are looking for. A record container node is the root node of a record subtree. It is the highest node on the DOM tree, such that it contains only the information of the record or its nesting records. For example, the I2 is the container node for record 1, and I16 is the container node for the record 2, because it's the highest node that contains records 2 and its children records. Our method is based on two types of common structures of web records, and we call them web record invariants. The first one is named invariant subtrees, which is a subtree structure that presents and serves the same purpose in every web record from the same logical table. For example, the thing of the record 1, 2, 3 all have the same structure in the subtree. And the second type of invariant is named invariant path. It is defined as an identical path from the invariant subtree to their corresponding container node. We try to use invariant subtrees to locate web records and use invariant paths to determine their boundaries. So with the invariant subtree and invariant paths, we define two assumptions. First, web records in the data region of a web page contains one or more non-trivial invariant subtrees, and web records in the data region contains one or more invariant paths. And here we have a quick overview of our approach, and we will introduce them in detail later. Our first step is to transform the DOM tree into a node sequence, and then we encode each node into a code with an appropriate scheme. Then we search invariant subtrees by mining frequent patterns on the code sequence. And finally, we recover web records by aligning invariant subtrees and invariant paths. In this paper, we compare three different node encoding schemes. The first one is HTML text path encoding, where a node is represented by its text path from the root to the node. And this encoding scheme is frequently used by existing works, but it does not handle the nesting structure well because the take paths of the nesting web records are completely different from those non-nesting ones, and thus the invariance of trees will have different encoding sequence than those non-nesting ones. So to overcome the problem, we propose the signature encoding where a node is represented by its tag name followed by attribute names. And we also propose structure encoding where we encode a node by its subtree structures. With the node encoding sequence, we want to mine frequent patterns to find invariant subtrees. This is a classic frequent pattern mining problem and can be solved using suffix tree. I'm going to skip the process here due to the time limit, but you can find details on our paper. And then we select closed patterns. We choose closed pattern because we are following the a priori property. And then we reduce pattern length to guarantee a pattern is within a web record. This step is important because sometimes a pattern can go beyond the boundary of a web record as we show by the example here. But we know the invariants of tree are always substructures inside a web record. And then we can map pattern back to the invariance of tree on the DOM tree. Once we have the frequent pattern, get the invariance of trees from the frequent pattern, we try to reconstruct web records by aligning the invariant paths. I want to emphasize here the mapping a frequent pattern back to invariance of trees is not a trivial task, and we have to skip the details here again due to the time limit. Now, with the invariance of trees, we keep comparing their parent node, and then we throw away a subtree if its parent is not the same as the majority. We will demonstrate with the frequent patterns they extracted from the structure encoding sequence. So the frequent pattern are mapped back to these trees here, and we have a false positive here, which is due to the advertisement. And then we try to keep going, comparing their parents. And in the first step, we see that the parent of this advertisement is different from other invariance of trees, so we throw it away. And then we keep comparing the parents again and again. And at this step, we find a node that contains all the invariants of trees. That means that we have reached the boundary of web records, and we stop here. Here we briefly discuss the performance of Myria. We compare Myria with several existing methods on datasets of web records across different domains. The first dataset, TBDW here, is a comprehensive web records that were collected about 20 years ago. And then the EX is another comprehensive dataset. They are collected recently. And we also collected Amazon, Google, and Commons. We found that Myria has a competitive performance on old style web records when compared with the existing methods. But when it comes to the new style web records, Myria has the best performance, and the performance is consistent across different datasets. And finally, we notice that the existing method have significant record loss when there are heterogeneous schema or nesting structures. And this is particularly significant in terms of Google dataset and the common dataset. As we can see here, the record is pretty low. This work is supported in part by 3 US NSF fundings and also a gift from NVIDIA Corporations. And this concludes the presentation, and thanks for watching.